I think it is recording. Yeah. Okay, so just previous recap, we have studied about those things. Now today we are actually going to solve some questions also, as well as the deep study about the properties of the laser. Okay, so laser basically, as we discussed, is having the high monochromaticity. High monochromaticity means it will have only one frequency of the light, and also we say a narrow spectral width. Okay, so here you can see this is monochromatic light where it has a single wavelength of the light. Okay, so when we say non-laser light, like the light source which is coming from the sun. So once it passes through the prism, it will have the seven wavelength of the color. So that this we call as a polychromatic light. But here for monochromatic, you will have the single wavelength of the light. And I hope you have studied about the Young double slit experiment. So how we can extract the single wavelength of the light when your entrance light source pass through a small slit with then it will have some dispersive medium that will disperse the light in particular wavelength of the light, and through a small exit slit one wavelength of the light will pass through. So this is how we can produce the monochromatic light. So here if you are changing the dispersive element rotation of the angle, the different wavelength of the light can be extracted. So this is the first important, is the highly monochromaticity of the light. Second important thing is the coherent. It will be important for your exam. That's why I'm saying it is. This is the main property for your properties of the laser. So coherent we will also study in the deep detail, where we will able to see that what's the difference between the coherency and the incoherent source of the light, where it has a variation of the phase as well as the amplitude. Okay. Then here third property is the collimated source. Collimated source means where you will have the parallel beam of the light, and divergent source means you when you will have the mm, a non-parallel source of the lights, which we obtained in the torch or in the bulb, where in collimated light we obtained only in the case of the laser. And also the high intensity laser light has a property that it will emit as a high intense source of the light. Why? Because we amplify the population inversion at E2 level, where you will have the most of the electron at the excited state, and we are applying externally some sources so that both the emitted light, the emitted photon will not be only one single, it will have two times. So basically we are increasing the photon energy source, and that's why it has a high intensity of the light. Okay.
ഒമ്പത് പേരുടെ ആൾക്കാരൊന്നും ചരിത്രത്തിലാകും.
Hi, hi Simal, your mic is on. Can you switch it off? Yeah. Okay. So next, so what we are going to see about the monochromaticity, that we call as a very narrower range of the frequency or the wavelength. So here you can see that the x-axis is representing the frequency and the y-axis is representing the intensity. Okay, so if you are considering this point as a zero, okay, and you have a wavelength of the light, so you can see from this figure is like if you have an ideal monochromatic light, you will have the single wavelength. So you can see that this is the particular wavelength the x-axis is representing, and it has a high intense source of the light. But when we say that the light, but when the light is not an ideal monochromator, okay, so what it will have? It will have the range of the wavelength. Okay, so you can see that it has now at particular point different range of the wavelength and different intensity. So this range of the wavelength we call as a bandwidth. Okay, so this range of the wavelength is basically called as a bandwidth, and the distance is defined by delta lambda. Okay, this you people carefully understand it, because next we are going to solve the questions, numerical questions also. Okay, so this is basically the narrow range of the wavelength, and it emits and we call as a bandwidth. Okay, so if we talk about what is the absolute monochromaticity wavelength range, so you will say that it will have the difference will be zero. So you can see that it doesn't have any range. It has only single wavelength of the light. Okay, so absolute monochromaticity light always have delta V is equal to zero. That people can ask in the MCQ question. Okay, now the thing is, what is this representing? This was in the form of the wavelength. The x-axis was in the form of wavelength. But if you convert into the frequency, it will be remain same. So if you are considering the frequency of the light with the intensity at a central point is defined as the central frequency and denoted by nu naught. Okay. Now this is the case of the ideal monochromator. Now if you are taking the monochromator, other monochromator which is not ideal, so it will have the range of the frequencies. So these range of the frequency, suppose this point and this point, this left and right point is indicating how much the variation is from the central frequency. So that's why the central frequency you have nu naught, and how much the variation is differing, nu naught minus delta nu by 2. Sorry, here it will be plus. Here, this will be plus and this will be minus. Okay. Uh, Yeah, so here this is representing the maximum frequency of the range of the your monochromator. And when you are going left side of the central frequency, then you will have nu naught minus delta nu by 2. Delta nu is basically representing the difference in the variation from the central frequency. Okay, so this is delta 2. Sorry, delta nu is whole. This line, when you are dividing by half, then it is taking only this much. Okay, from central frequency. So this is delta nu by 2 and this is delta nu by 2. Whole will be delta nu. Okay, so now here the band which is coming from monochromator consists of a band of the frequency which are closely spaced around the central frequency. Okay, and this nu naught is also called as a line width, bandwidth, or frequency spread. Okay, now if you have to calculate how much the degree of the monochromaticity, so basically if you have to calculate for ideal monochromatic light, what will be the degree of the monochromaticity? Can you tell me? Can anyone tell me? As I told here, you have a ideal monochromatic light, right? So for ideal monochromatic light, the range of the frequency will be 0. So what you will do if you have to calculate the degree of the monochromaticity, what you will do? Delta nu is equal to 0. Here you will put 0. So the degree of monochromaticity will be 0. Okay, for ideal monochromatic light. But if we are seeing for ordinary light, what's the range of the frequency we get is 10 to the power 10 hertz. But for the laser, the variation is very less. The change in the frequency is only 500 hertz. Okay, so if we have to calculate the frequency bandwidth of the laser, so frequency bandwidth means delta f. Delta f is also representing delta nu only, which is equal to C delta lambda upon lambda square. Okay, so how is this formula basically coming? Okay, so basically if you have to understand from where delta f is equal to c is delta f is equal to c lambda delta lambda upon lambda square. Okay, so what you will do, we know that if you have to derive it, what we can do, suppose if I'm taking here we know that nu is equal to c by lambda. right? If you are differentiating dv, derivative if you are taking, so what will happen is like 1 upon delta derivative is equal to lambda upon lambda square. I think you know d lambda here. You know the derivative, at least you have studied in the mathematics, okay, and you are physics student, so obviously you know. So delta v is equal to the c by lambda square into delta lambda. So you can see that it's nothing else. If you have to calculate the frequency bandwidth, we have just taken the derivative of this, and now it is validating with this formula. Okay, so this is how it is coming, the frequency bandwidth of the laser. If possible, you can write the formulas at least from in your copy. Just now, right now only you write all the formulas. So next it will be able for you to understand how the things is happening. Now another thing which I wanted to convey you is like what will happen if you have a if it is given that in the form of the frequencies, right? So if I am giving you in the form of the wavelength also, so spectral line width are the bandwidth in the wavelength number. So what you will do is like here delta lambda upon lambda, the initial incident radiation of the light. So this is representing your degree of the monochromaticity. Okay, degree of monochromaticity. Okay, I think I will suggest you to write the formula right now so that in the next slide, it will be easy for you to understand properly. Because I am going to uh, ask you the question. So next, this is what I was telling you to solve it. So first question, which is giving you, it's a simple only based on the previous formula. A laser which is emitting the light with a peak wavelength of 589. So peak wavelength, it is given. Peak wavelength of light 589. That means lambda is given, right? Lambda is given. So what is the spectral line width? Spectral line width means delta lambda. Okay. If the delta lambda is asking if the intensity drop to half its peak value at 588.8 means lambda 2 minus lambda 1. It is representing delta lambda. So the peak value is dropping 588.8 and 589.2. So 589.2 minus 588.8. Okay, because lambda 2, lambda 1, we have range of the wavelength. Maximum range of the wavelength is lambda 2 and minimum range of the wavelength is lambda 1. Okay, so did you understand or not? So from figure also you can see, let me go previous slide. Yeah, so here instead, this is maximum value and this is the minimum value. Okay, so this was the maximum, this was the minimum. So if you are converting this in the form of the wavelength also, so this is representing the lambda 2 and this line will represent lambda 1. So delta lambda you can calculate by lambda 2 minus lambda 1. Okay. So this is what it is asking. So once you will subtract it, what it will come? 0.4 nanometer. Okay. And this was the answer for this question. Okay. So can you able to solve next question, second question? Just try it. I will give 2 minutes of the time. Anyone can solve and let me answer. Tell me the answer also. How did you solve? At least please be interactive in the class. Don't worry whether it will be wrong or right. Nobody cares. Okay. I can give you the hint also. It is using the previous formula only, nothing else. So what it is given is that if a light source has a spectral line width of 10 nanometer, spectral line width of 10 nanometer means delta lambda is given 10 nanometer. Okay. And a peak wavelength of 650 means lambda is also given. Okay. So what is the relative spectral line width? That's it. You have to just calculate the percentage. Are you getting this percentage value? Guys, you people are not speaking at all. At least yes, no, tell me.
Yes, ma'am.
So you are getting, so what you have to do is 10 divided by 650 into 100. If you will solve this, I think you will get 1.54 percentage.
Yeah, ma'am.
Yeah. Okay. Then next question. Next is also easy. Next is also nothing else. Okay, what it is given is if a laser emit light at 500 nanometer. So lambda is given 500 nanometer. Okay, with a line width means delta lambda 0.0002 nanometer. Okay, then compute degree of monochromaticity. So monochromaticity, as I told you, delta lambda by lambda, degree of monochromaticity, delta lambda by lambda into 100. That's it. Sorry, here 100. So you will get this percentage value. So if you have to calculate the degree of monochromaticity or spectral relative spectral line widths are the line width only. This is the example where you can easily able to solve it. Okay. So next question is little bit long, but it will be covering of all the formula. Okay. So let's read this one. This I think you should solve it. Here I have not written the answer also. You should tell me. I also don't know the answer without solving. It will be little longer, but I think you will be able to solve it. Just use the formula. So what here is asking is basically the spectral line width increased to 0.1 nanometer. That means delta lambda is given 0.1 nanometer. Okay. Keeping the central wavelength 532. That means lambda is given 532 nanometer. So how would that affect frequency bandwidth, degree of monochromaticity, and frequency ranges? Okay. So frequency bandwidth formula, we have bandwidth formula we have taken just now we have seen in the previous slide. Mm, this one, the frequency bandwidth of the laser. So write this formula delta F is equal to C delta lambda by lambda square. So what's the formula? Delta F is equal to C delta lambda upon lambda square. You have all the things. So you can calculate the frequency bandwidth. Can anyone calculate and tell me what's the value it is coming? Guys, anyone is solving? It's a simple math. Just you have to put the value.
Ma'am, 1.06.
1.06. Yeah, it is correct. Tell me 1.606 into
10 raised to 11.
10 to the power 11. Yeah, it is correct. Okay, so this we have solved frequency bandwidth. Very good. Now the thing is next is the degree of the monochromaticity. This is also simple. The formula you have to use. What's the formula? The degree of the monochromaticity. I'm writing dm, that is equal to delta lambda upon lambda into 100. Can you tell me what's the value coming? Anyone get it? Anyone solved it or not?
0.018%.
Yes. Yes, 0.0188 percentage. Okay, now next is the frequency range. So frequency range is asking. That means what it is saying is that you have to find the maxima and minima. So here we have seen the maxima value and the minima value. So what you will do is basically plus delta V by 2 and minus delta V by 2. But here you have a wavelength. Okay. So you need to convert it into the frequency. Or you can convert directly in the lambda minima is equal to lambda minus delta lambda by 2. Okay. By 2. And for the maxima, lambda plus delta lambda by 2. That is the value. How much you are getting?
Delta minimum is 531.95.
Yes, correct. And lambda maximum, I think 532.05. No?
Yes.
Yeah. Okay, fine. Then, okay, so we have able to solve the question. So now we are going to start another topic which is important and a part of the laser only. That is the continuous and the pulse laser. Okay, continuous from name only we can say that you will have the continuous intensity of the light source without any variation in the intensity. Okay, and pulse laser means you will have the intensity of the light for some time. Pulse means in a form of some, for the some time the laser will emit, after that it will not. Then again the pulse start, the laser will come and then it will not come. So from the figure also itself you can understand. Here you can see that you have a continuous light, but here you can see that here up to this that much, then here the gap, then light, then this white gap, then light, then this light. So we are giving the in the form of the pulse. Pulse means for some time the light will emit, after that it will not emit. Then after that again you will on, then it will emit, and after that it will not emit. So it's a kind of pulse lasing method. Okay, so what is basically this continuous laser method? So continuous laser, you can see that whatever the power output it comes, it will be continuous of the same intensity, same power with time. And with the time, it is not changing at all. So a continuous laser emits a steady and uninterrupted beam of light over time. And the power output remain constant as long as the laser is on. So what are the important feature of this continuous laser light? You will have the constant emission of laser light. Simple. Okay. Power will be steady over time and used when consistent illumination is needed. Okay. So what's the application? So application is very much, I can say, and it is the most kind of the most typical kind of the laser you can see people are using. So basically in the cutting and welding purposes, we use, because it has a continuous emission of the light laser, and also in the fiber optical communication, for the communication purpose also it basically used. And we have seen this thing I think everyone has seen this barcode scanner wherever we are going for buying anything, or shopping malls or anything, with these people used to take this machine where you scan it and allow you to enter it, or like for purchasing accessories or anything. Okay, so this so you I think you have never know it, that what kind of the laser they that is. So it is basically a continuous laser is present in this barcode scanner machine. Okay, also this is used in the molecular spectroscopy. Molecular spectroscopy means if you have to detect the molecular properties, so you can emit your light source continuously, and you can get the spectroscopy or the fingerprint imaging of the molecule, which are what kind of the molecule are present in the solution, or the in whatever you are interested to detect it. Okay, so it is very so in spectroscopic technique, basically if you have to identify any molecular species, this continuous wave spectroscopy is very much important. Now, second is the pulse laser method. So pulse laser we were talking about is basically emit the light in short, high intensity burst or pulses rather than continuously. Okay, so as I told, this laser basically emit the light in the form of the for some time, and after that stop it, then again it will rise, then stop it, again rise, stop it. Okay, so like this in the form of the pulses, for short time it will come, but it will be high intense also. And the duration of each pulse can range from, or uska duration, what's the duration basically is the nanosecond to the femtosecond. It says that that pulse duration is very small, right, in a nano and the femtosecond, and it basically depend upon your laser condition. Okay, so laser condition. So a key feature if you are talking about is similar to continuous wave. If you have emit light in the form of pulses, not continuously, much higher peak power than the continuous wave laser, and controlled pulse duration and repetition rate. So where you can use this, I think this kind of the laser basically used mostly in biology purpose. Suppose here the laser eye surgery. Okay, so laser eye surgery we need. If we are using continuous wave laser, what will happen? We don't know that when the how much amount this laser intensity is interacting with the tissue. So if you are putting continuous, it might affect some other tissues present beside the disease which we want to remove it. Okay, and it can be over impacted our eyes. Okay, so that's why if you are putting pulse laser, what is the benefit is that if you are giving that amount, and if you think that it can go more deeper, then you will stop it. Okay, so you will stop it, and it will not affect more to the eyes. Then in the lidar and the range finding means like a Wi-Fi system. The Wi-Fi basically it's a lidar only. If you have your phone is suppose you are sitting inside the car, and your phone is you have to detect the other areas people phones or anything you want to check nearby range. So It's a range finding. So in that also we use laser only. It basically work on the principle of the laser, and it is a pulse laser method. Okay. Now the material ablation and micro. This is part of the your what to say so this is also a part of your medicinal purpose only. If you are putting the laser light, how much depth you have to cut it, or what kind of the shape you want to give it, that you can design it. Okay, so here basically PDMS is there. PDMS is basically solid, but you can convert it into the liquid, liquid also. And then PDS, APS, this kind of the polymer, I think it is. So if you are putting the laser on this, that much high source will cut and give you a design shape. So it is basically used in the micromachining technique. Then another is the time resolved spectroscopy, means at that much frequency of the light, means time resolved now. So time resolved means suppose you have one molecule. Okay, you have this molecule and it is undergoing in the excited state. So how much, what time, means that excitation happen in what interval. So how we can, you can able to probe it. So this you can able to probe using this time resolved spectroscopy. And when it has to undergo de-excitation also, that also you can able to probe it. That's why it is called as a time resolved spectroscopy, that give the kinetic profile and the reaction intermediate information. So here you can see that this is the reaction intermediate information. You can get it from the time resolved frequency. So right now it's like a terahertz, that much range of the frequency uh, of the laser. We probe it on some substrate or whatever we are interested to detect their excitation or the de-excitation of the molecule intermediate state. Okay. So now the second property we are going to discuss, that is based on the coherence. Okay. So today we will read about the properties only. We have 7:15, na? We have time. Okay. So now it is about the coherence. Coherence, as I told that, it's a simple, nothing else. What you have to think is the phase difference. Okay. Suppose you have this particular wavelength of the light or the amplitude of the light. Okay. And you have another. So if you are seeing this wave amplitude, this amplitude, and the phases, both are in the same. So that's why we call this thing as a coherent. Okay, so wave nature of the light, two wave of the light, both are in the same phase, then we call as a coherent. Now if you are seeing this position, you have amplitude in the positive, but here you have zero amplitude. So that means the phase has shifted. So you had this thing now here. So that much shift has occurred. Okay, so that much shifting has occurred here. Okay, so this we call as a change in the phase. So if the change in the phase difference is occurring, that means it is a non-coherent. Okay, so coherence by definition, we can say the degree to which a wave maintain a constant phase difference. Okay, this we can see also in the young double slit experiment. Like you have studied the light source when it is passing in and entering into the slit, then it basically form the constructive and the destructive interference. So constructive, where you will have the brightness of the light, and destructive, where you will have the dark spot. Okay, so constructive destructive interference kind of the feature obtained in your screen. And if we are talking about the application, so we can use this application in a holography experiment, which I think you may have not seen in your real life, but you may have seen in the movies, especially Hollywood movies, like Marvel movies also, I think you have seen it, and many more where they are using this holography method to detect the for the medical purpose or any other things, are the locating something. Okay, so for that also you can use. So coherency is a matter to you. If you will not have the proper coherency, you will not get the proper designing of your molecular feature or the whatever you want to detect it. Okay, so without coherence, interference will disappear. Okay. So next, yeah, here is the deep detail. So in the coherence also the two things comes. What is the coherent time and the coherent length? Okay. So the two things that comes is the coherent time and the coherent length. So what is basically the coherent time? Coherent time means from the meaning only we can understand that the time up to which your phase of the wave will be same. Okay, so here you can see that this is the phase, one wave, and this is the second wave. So up to this much time, the time duration, the wave light or the light maintain a predictable phase relationship with itself. Okay, and it is defined this phase coherence time. Tau c is representing the time is depending upon the delta v. Delta v in nu is that is the frequency. Okay, it is inversely proportional to frequency. That means if your frequency is higher, then you will have the coherence time very less. Okay, why very less? Because suppose I am saying that you have a like this kind of the frequency of the light, and I am saying that it is normal. Suppose it is some new light. Okay, I am saying that now you have a frequency of the light like this. So this is having higher frequency, right? So it has have higher frequency. So higher frequency is having now the phase time is very less as compared to this time, right? So that's why it is having the inverse relationship. Okay. It is having the inverse relationship. So from spectral intensity comparison also you can understand this is the sunlight. I think I have to erase it. This one you are not able to see. Okay. Yeah. Okay, so here also you can see sunlight. Sunlight is having some relative intensity like that with the wavelength. So that's why here you can not able to see the any kind of the phase difference or other thing. But if you will zoom it, you will find something. So if you are zooming it, that means at very less timing, you will have the coherency. Okay, so that's why the sun has a coherence time of few femtosecond. Okay, and if you're talking about some xenon or laser diode or LED is having a very sharp single wavelength of the light. So it has a so if you're talking about all other lasers, so laser with very narrow range of frequency range of basically millisecond only. Okay. So this is about the coherence time. Next, that is important is basically the coherence length. Okay. So previously we were talking about the time based. Okay. Now we are talking about the length based. Okay. So the length based, if we are talking, so the distance over which a wave remain coherent. Okay. So wave remain coherent means phase will be stable up to what distance? Means I'm saying that you have sorry. Uh, I'm saying that if you have suppose here from figure only, if you have this wavelength of the light, so this is the length which is representing LC. Okay, so at what particular length of the light, this phase intensity or the wave nature of the light is not changing. Okay, so this length is demonstrated by the LC and it depend upon your coherence time as well as the velocity of the light. And if you are solving this, you will get the frequency. Okay, so frequency is having direct correlation with the coherence length, but frequency is having the reverse are the inverse relationship with the coherence time. Okay, so it is just opposite. Okay, so basically higher laser will have the length of the kilometer, length of the kilometer of the coherence length means and LED will have the coherence length of only the micrometer. So what I'm are you understanding? This is like simple only about the coherence. It divided into two part: coherence time, coherence length, and now it has further divided into two category. I will not say category, characterize. It basically categorized into the spatial and temporal coherence. So spatial means space. Spatial means space. When it is coming space, that means length is coming, right? Now temporal means very for the short time. Okay, so it is time dependent. Okay, so spatial coherence means length dependent and temporal coherence means time dependent. Okay, so what is basically this is? Okay, so here we will going to study about the difference between the temporal coherence and the spatial coherence. So what I said is that temporal means time based, right? And spatial means space based. So temporal, here you can see in this figure, you can see all the amplitude of the light is having a particular phase at particular time. You can see, right? So this is x-axis is representing the time. Okay. So at infinite time, this is having a same phase. Okay. So what we can say that it has a infinite temporal coherence. Okay, why? Because both the wave maintain a constant phase relationship over time. But if you are talking about this graph, okay, what it is representing is that you have a parallel lines, right? But these parallel lines widths are, you can say, are almost equal, are equal only. Okay, so these lengths are almost equal, and this equal is like going infinite. That means coherence length is infinite. So that's why we say that infinite is spatial coherence. Okay, so so wavefront moving through space with parallel and equally spaced plane, and the vertical spacing and consistency across space suggest infinite spatial coherence. Okay. Yeah. So this is about the difference between the temporal coherence and the spatial coherence. Okay. Now the thing is you have to differentiate with this figure and where this kind of uh, the coherent system we can apply. Okay, so it is just you have to just keep concentrating for small time. You just keep concentrating. What I said is that spatial means space, right? And time, the temporal means time dependent. Okay, so here you can see this is the axis given, the time and the space. Okay, that is the distance. So if you're talking about this kind of the wavefront, we can see that it has equal distance, right? Equal distance. And it is infinite. So we can say that LC, coherence length, is infinite. When we are talking about spatial thing, means the x-axis, sorry, y-axis, the space, if you can see, all the waves are in a parallel and zero phase, right? So in the zero phase, that means, and it is infinite also. So coherence time, if you are talking about tau c, that is also infinite. So this is where we can all obtain infinite coherence and infinite coherent length and time when we are using the ideal laser beam. Okay, when we are using the ideal laser beam, then we can able to get the infinite temporal coherence and the coherence length, and the spatial and temporal both are in a coherence. Next figure, I will delete this one. I think it will be easy for you. Okay, so here now the thing is next, which is second is saying that I have a temporal coherence only, but spatial is incoherent. Okay, temporal is coherent and spatial is incoherent. Then how it can be possible? So now we are going to see this thing. Okay. So as I told, as temporal means time dependent. Time is our x-axis, you can see, right? So time based, if we are seeing, what it is telling me that at each interval having equal width, it is changing, right? Huh. It is sorry, all are equal widths. So it is not changing. That's why we are saying that it is a temporal coherence. Okay. So it is a temporal coherence. Now the thing is, we are here, they are saying that it is a spatial incoherent. Spatial means with the space. So that means y-axis we will consider. So if we are seeing the wave nature, this wave nature, if you are seeing, it is varying. It is not equal with the distance also. Okay. So what we can say that it is a temporal spatial incoherence. With space, in within the space, it has incoherency. Okay. So now next, if you are seeing, spatial should be coherence and temporal should be incoherent. So how we can detect? We can see here also that it has a smaller weight, then larger, then smaller. Okay. And not equal. So that's why we are saying that it is with the time it is changing, right? So it is a temporal incoherence. But length, if you are talking, both all the wave front is having zero phase. So that's why the spatial coherence length will be infinite and the time will be incoherent. Okay. So this is the example of the coherency and incoherency based on the spatial and the temporal. Now, if you have to get spatial and temporal, both are incoherence. Then you can see both is these both are having different length, width, and also the phase are changing with the time. Okay, so that means it don't have anything, either spatial or either temporal. Okay, so as we have discussed, if you have the infinite temporal coherent length and coherence time, then you will have you are reaching to the ideal laser beam. But if you have only temporal coherence, means time dependent only, then what you can do is multiple small uncorrelated sources emitting the same frequency. There only you can use it. Then if you need temporal incoherence system, then the light which you can use having uniformity only for shorter time. Okay, that kind of the flashlight you can use. But if you don't, if for, I'm saying that you don't have spatial and temporal coherency, then it can be anything, sunlight, bulb, or any kind of the thermal light. Okay, so that means from the sun, what we get both spatial and the temporal incoherence wave of the light. But when we talk about the laser, you will have spatial coherence also and temporal coherence also. Okay, I think you understood about the this mechanism. Then here also I have put some questions that you can able to solve it, I think. So it's a simple only. I think you can able to understand what's the factor basically determine the what's the factor basically determine the coherence length of the light source. Coherence length, as I told, it depend upon the frequency, which is equal to the C into time. Okay. So where it is depending? It is depending upon the spectral width of the line. Okay. Also coherence time, and also how much stable your light source. Okay. Stability of the light. I think you should write it in the copy. Maybe it can ask in the questions examination. Stability of the light also. And the uh, what I can say other is the emission mechanism, how the light is emitting. So these are the factor on which this coherent length of the light can depend upon, right? So next question, what it is telling, it's a numerical question, right? Yeah, it is based on the formula only, I think. So spectral bandwidth have delta nu, that much. Calculate coherence time and coherence length. It is simple only. So coherence time, what it was, tau c is inversely proportional to delta v, and coherence length LC was, I think, c into tau c, right? Can you able to solve it and answer me how much it is coming? I think Hridaya and Avantika, these two are at least speaking properly, answering the questions also.
TC is equal to 3.33 into 10 raised to minus 13.
It is correct. Correct. Yeah, this is correct. And LC?
0.0001.
Yeah,
0.001
0.0001.
0001. What? It is in a meter or what?
Yeah, meter.
Then meter it is fine. That means 0.1 millimeter, right? Yeah. Now again, the next question is basically, it's a simple only, but it has a detailed structure information. Okay, so what it is telling me, let me delete this one. Okay, so here, so what it is telling, a laser has a spectral width, and spectral width means delta lambda 0.001 nanometer is given, and at lambda is given 600 nanometer. Now an LED has a width of 20 nanometer at the same central wavelength. Okay, so at the same central wavelength only, for the laser, this is for the laser. Okay, this is for the laser, but you have others light source also, which is LED. So LED width, if they are saying delta is 20 nanometer. Okay, same central wavelength means 600 nanometer. Okay, so which has a greater coherence length and why? So coherence length, it is asking coherence length, what is the formula? This, right? It's this. Okay, so this is the coherence length formula. So what you have to do is basically, okay, let me erase this one. Uh, yeah. So the question, I think you have understood what it is telling. Okay. Yeah. So it is given that we know that coherence length is equal to C into tau C, right? This we know. Okay. If we are solving and the tau C is equal to 1 upon delta V. Okay. So if we are replacing tau C by 1 upon lambda, so 1 upon delta V, that means C into delta V. Okay, we have to convert it into the wavelength. So V is equal to nu is equal to C by lambda. Okay. Nu is equal to C by lambda, right? So what we can do is basically delta, it will be delta lambda, right? And then we can convert it into 1 upon delta lambda. If you solve this C, nu is equal to C by lambda. So that is nu into lambda into delta C, delta C will not be by lambda. Okay. So again, this we can replace by nu square lambda square, right? Yeah.
Excuse
So
me,
nu, ah,
the LC is equal to C into TC. So C into 1 by delta V, right?
okay, yeah. 1 upon delta lambda V. So here, that's why I'm saying why it is coming opposite. Okay, so it will be 1 upon, right? Here it will be lambda only, sorry, nu only. Okay, so this will come, right?
Yes.
Ah, oh, sorry. So delta lambda, it is fine. Now delta lambda nu is equal to C by lambda. So C will be here and delta lambda will be above, right? So okay, let me erase from one thing. Thank you for reminding me. I was just thinking something else. Okay. Oh, yeah. So LC is equal to tau C into C. Okay. 1 upon delta V into C. So delta V is equal to, we can write nu is equal to C by lambda C by delta lambda. Okay. So this will be here. Okay. Sorry, delta C. Delta C is equal to the so here it will be C delta lambda. When you will solve it, what it will come is not this. Okay, sorry. So eraser. When you will solve it, then it will come lambda square on delta lambda. Okay. So LC is basically equal to the lambda is not square by delta lambda. So when you will put this value, you have given delta lambda also and you have given lambda also. Okay. So if you are putting this value, ideally, physically, we know. Okay. What we know physically is that laser will always have higher coherent length. Okay, as compared to the LED. We just what we need is basically the ratio of the coherent length. So when you will solve this, I think if we are solving, let me erase this something. Okay. Yeah. So if we are erasing this, what we if we are talking about for the laser only. Okay, LED. Chalo, we will talk about LED. So 20 nanometer divided by where it is 20 nanometer divided by length width is 0.001 nanometer, right? This is okay. So this ratio and this ratio we have to take it. Okay. So how much it will come? I think 20,000. Yeah. So it is basically like 20,000 times higher as compared to the laser. Okay. So you can say that the laser is having 20,000 times higher coherent length as compared to the LED. Okay. So as we already know it from ratio, you can able to get it like what will be the coherent length. ratio of the coherent length as compared to the laser and the LED light. Okay. So next, if we are seeing is the collimation. This will be very small. Collimation, what's the time? 7:41, just 2-3 minutes. Collimation means you will have the parallel beams of the light. Here you can see that all the waves are emitting parallelly with each other. That means it has infinite coherent length. Okay, also the phase. So temporal and the spatial both are validating. So parallel beam of the light. So light travel in a parallel direction, minimizing the spreading as they propagate. So what's the benefit? Benefit is that it has a narrow beam, focused spot, less attenuation, which is important for any kind of the surgery. Okay. Next is the collimated lens are used. So if you have to make it parallel beams of the light, how you can make it? By using the collimated lens. Some lens are used so that you can able to get the some optics principle they have used of using the lens, and they will be able to get the parallel beams of the light. So directionality and no divergence. Okay. And if you have to calculate the intensity and the power, it has a relation with the intensity, direct relation with the power, and square of the wavelength relation with the reciprocal of the square of the wavelength relation with the intensity. And the unit is watt per meter square. Okay. So this is about collimation. Now, I think this we will stop. Laser acting medium. I think let's see what other we have. Okay, so kind of the lasers and other thing. Okay, so we will study in the next class what it is. Okay. Um, yeah, so we will start with the solid state laser. Okay, next, and then we will discuss about the focal length of the lens, and we will do the numerical questions on that also. Then what's the application of these kind of the laser? That also we will study. Okay. So for today, I think it is over. I have to take the attendance also. Um,
I have the question in the last question we did.
yeah. Tell me.
Can you show the slide? I had a doubt in the steps.
Yes.
The same lambda, delta lambda by delta C,
Hmm.
how is it converted to lambda square by delta lambda?
Oh, okay. So basically, I did not calculate it from here. So basically, the formula basically comes from the this frequency width of laser, which we have studied, right?
Yeah.
Uh, it has, I think, which slide?
Delta F is equal to C
Yeah,
delta lambda by delta.
yes. So from here only directly, I have taken it from here, but you don't need to solve that formula. I thought it will use that formula, but it was not required because you have to calculate it only the ratio. So estimating the ratio of the coherent length, so that just divide by this and this. Okay.
Okay, and what is delta V exactly? What does it
So
represent?
delta V basically, as I told here, yeah, the variation from the central frequency. Okay. So this is the delta V. Okay. So from figure only, if you are understanding, this is delta nu, right? This portion only. This is your delta nu by 2. This is delta nu by 2. This much and this much. So if you are talking about total, so how much the range of the frequency from maximum to minus. So delta V is basically V maximum. What's the value of frequency at this point? Minus what's the value at this point? V minimum. This is the delta V. That's why we are saying the range of the frequency basically. Okay.
Okay, thank you.
Yeah. Okay. Good. I think this class you liked it. We have solved so many questions. So next we will study in the next class. Okay. Okay, then I will stop sharing or stop recording first. Stop recording. Yes.